So I want to go back to this idea of defining functions using either by cases or equations. And here we have kind of a basic defining equation. Right, that's what I've been calling them. This is how we define a function, okay? But I really want to ask the question, what does it actually define a function, right? Maybe it isn't true, okay? So here's what I can guarantee, and this is a different perspective, is that at the very least, this is something that tells me some properties that max n must have. As an example, I might give you this property. Max n of x followed by x's, okay, must be greater than or equal to x. That is a property, okay? It is not a defining equation. It doesn't define what max n does. It just tells me something that's true. So I might remind you of things called little theories, okay? So these are things that we really expect to be true of our code, right? They're properties. They're not necessarily full-fledged definitions, okay? We can call them a specification of our function, right? And that's kind of a term from software engineering where before we write something, we try to specify what the function will do so that we can then say whether we actually succeeded, right? You know, whether our function actually works. You need to have something to go against. The term specification seems to implies that is a complete specification, right? But often that's not true. Okay, so for example, you might talk to a client or your boss. You're supposed to write some software, and they'll tell you, we want you to write a program that does this, this, and that, right? And you listen to them, and you understand what they want, and then you go off and you start trying to build it. And what you find is that you have a lot of questions. You know, there's many things that they did not tell you, right? That's because the specification is not complete, okay? And so you have to go back and ask questions. Well, what do we do in this case, right? Okay, so that's kind of the distinction that I'm making between a specification, which could be incomplete, right? Even though the language implies that it's not, but in practice, it often is, okay? And then something like a definition, which is always complete. Okay, so how do we know whether our specification is actually a definition? That's the question that I want to pick up and address. Okay, so here are some of the things that can go wrong. Okay, maybe no function satisfies it, right? So what we might say is that what we have is a contradiction. Okay, so maybe you're giving two different requirements that go in completely against each other. Like you might be told, for example, that if you have a really tall person, you should refer them to the big and tall part of the store, right? But you also get a requirement that says that if a person is a VIP, then they should go to the VIP part of the store, right? And as you're coding, you go, hey, wait a minute, what if I have a tall VIP? You can't fulfill the requirements. You can't do them both at the same time, okay? Now, another kind of thing is that more than one function satisfies the equations. And what that means is that there is some ambiguity, okay? So somebody gave you the specification and said, this is what I want you to build. And then as you're doing it, you go, well, what should I do when x is negative? They didn't tell me, right? So maybe I could return 0. Maybe that's the right thing to do. Maybe I should throw an exception and say, you know, this doesn't work. I don't know what's the right thing to do. That means there's ambiguity. Something is wrong, okay? Now, the final kind of condition is this. Maybe, you know, there's only one function that works, so we actually know what function we're talking about. But the problem is that we can't compute the answers because the way that the specification was written, it is inherently uncomputable. Okay, so I'll give you some examples of that so you can see what I mean by that. Okay, so here's the first example: f of x is equal to 0 if x is less than 0. So this is case 1. But look at case 2. F of x is equal to f of x plus 1. Okay, this can never be true. Because let's say that f of x is 3. F of x plus 1 is 4. 3 is not equal to 4, and so on, right? So this is a complete inconsistent, right? So this is the first thing that we talked about that could go wrong. So it's gone wrong here. We don't like this. Let's move on. Okay? All right, so here's another case. We have f of x is equal to f of x plus 1, right? Now, there's actually, this is ambiguous, okay? And that's because there are many functions that are possible. and you wouldn't know which one it is that we meant. Okay, so let's look at that. For instance, what if f of x is always equal to 0? That satisfies this equation, right? So that could be the f that we had in mind. Here's another f that we might have in mind. It has to be 0 for negative x because of this, right? So that's actually captured right here. Okay, for negative x, it's always 0, right? But how about for positive x? I could say that is f of x equal to 1. That would satisfy this equation, because notice that f of 2, for example, is 1. It's the same as f of 2 plus 1. F of 3 is also equal to 1. Yes, they're the same. So it would satisfy both of these equations, right? So how do I know which one it is, right? And then here's a crazy one. F of x could actually be equal to sine of 2 pi x. And sure enough, that actually satisfies these equations as well, okay? You can think of any periodic function that has period 1, and sure enough, we'll be able to satisfy both of these equations. So this is a case where it's ambiguous. There's just too many answers, so you wouldn't know which is the one that we mean, okay? Now here's the example where we have something that's just simply not computable, okay? So if we look at this, f of x is equal to f of x, right? There's only one function that satisfies this, because we have f of x and then we take away f of x, right? So the only function that will work is 1. Okay? Or rather f of 0 for negative, 1 for other values of x, right? That's the only function that will work in this case, right? But if you simply type that into, say, Java or C++ or Python or whatever your favorite language is, then when it tries to compute f of 3, it says, oh, that's easy, give me f of 3. So then I'll try to compute f of 3 again, and it'll say, oh, that's easy, give me f of 3. And I'll just keep looking for f of 3. It will never get out of that loop, right? So this is what we mean by not computable. Okay? So those are kind of the errors that can happen. Okay? So yeah, now let's try to find how we can guarantee that this doesn't happen. Okay? And we actually talked about this a long time ago at the beginning of the course. But I think it's going to make more sense right now, okay? So if we want a definition, we actually need the following. We need completeness, okay? So what does complete mean? What it means is that you must not leave something up to my imagination, because in that case it's ambiguous, right? So if you define it by cases, every x has to fit in at least one case, okay? So that's kind of the first thing that we desperately need, okay? Now the other thing that we need is to be consistent. Right. So consistent, what we mean by that is that if there's two cases that work, okay, then they have to agree on the value, right? So if you find absolute value of x and you say is x for x greater than or equal to 0 and minus x for x less than or equal to 0, right? They overlap on 0, but actually x and minus x are the same thing. That we're going to allow, okay? So that is a good definition, okay? And finally, we want it to be computable, right? And again, what does computable mean? It means that if I kind of take that and hand translate it into my favorite computing language and hit go, it'll actually return a value instead of being an infinite loop. Okay, so these are the 3 C's, right? This is the gold standard for being able to write a definition of a function using defining equations. Okay, now I think the first two are fairly easy to check, right? But the last one, computable, is kind of tricky, right? So how do I know that f of x is computable if I define it by cases? The answer actually is that there's no way to know in general, okay? That's called the halting problem in computer science. And the halting problem says that if I give you a function definition, right, and then I give you some inputs for that function definition, you really can't tell me in general, right, whether that function will terminate, will return a value, or simply go into an infinite loop. Now, of course, in some cases you can, right? Like if it simply says return 0 and it doesn't even look at the arguments, yes, it's going to terminate, right? But in general, right, if I simply give you a function written in whatever your favorite language is, okay, let's say Python, right, and I say, oh, what happens if I call f with the argument 3? Does it terminate, right? You find that you cannot answer that. The best you can do is try to simulate it, okay, and if it terminates, then you'll be able to tell me, yes, it terminates. But if it doesn't terminate, then you might continue forever, just trying to check. Well, maybe you'll stop at the next step, okay? So that's kind of a general computer science issue. Okay. Now, I did say that in some cases you can guarantee that it does terminate. For example, if it simply doesn't even look at the arguments, right? But there's some other cases in which you can, and that's kind of this is what I guess I would call this the sweet spot. Okay, because it lets me define lots of functions and yet it lets me check to make sure that they terminate. So here is the rule. Rule number one is that at least one case does not use f in a definition. If all of the cases says, and then call f of something, I call f of 3, and then I'm going to have to call f of something. And to compute that, all of the cases do an f of something. So I'll have to compute f of something. I'll just keep going down, and it'll never actually finish. I call those base cases. Okay? And the reason I call those base cases will be clear in the next module. Okay? And then what I need is basically something that says, and this is a fancy way of saying, but it says that the inputs are getting smaller. So for example, let's say that I'm trying to compute f of 10, right? And to do f of 10, I need to compute f of 9. And to do f of 9, I'm going to need to compute f of 8. And to do f of 8, and so on, right? So eventually I might need f of 1. And to do that, I'll need f of 0, right? But this one, I know the answer. This is 3. Okay? So what we have here is actually a descending chain. So we have that 10 is greater than, I'll say greater than or equal to 9, although I don't allow equal. Okay, 9 is greater than or equal to 8. Okay, 8 is greater than or equal to ... Eventually that's greater than or equal to 1, which is greater than or equal to 0, and then I'm done. Okay, so what I want is this less than or equal to be a well ordering. Okay. That's why I made it greater than or equal to, because remember, greater than is actually not a ordering at all, right? Now, why do I want it to be a well ordering? That's because well orderings don't have infinitely descending chains. So no matter where I start, after a finite number of greater than or equal to's, right, I'm going to end up at the bottom, right, which in this case is 0. Okay, so what we want is there must be some well ordering that makes the arguments get smaller every time that you call f of a new value. Okay, as long as that happens, then it's actually well defined. So for example, when we talk about maximum, we said the maximum of x followed by x's. Actually, you have to call the maximum of x's. See how something got smaller, right? You know, the length of x's got smaller, and length is a non-negative number, a natural number, and less than or equal to over the natural numbers is in fact a well ordering, right? So that's what we can define. That's what we can use that in definitions. And ACL2 will actually prove that it can find a well ordering where the parameters are getting smaller before it accepts your function definition. So if you simply give it something where that's not true, like f of x is equal to f of x, right? It won't accept the definition. You can try it.